Osmotic pressure. For our example, we have a U-shaped form, and in the center a selectively permeable membrane, and water on one side, and water and a solid, something else than water, on the other side. The water can go through, but not that solid. The membrane is selectively permeable, so a solid cannot go through. Osmosis is now the total net movement of water from one side over to the other side. The water is going from the place with lower solute concentration, so here's nothing, to the side with higher solute concentration, where a little bit is. And that is the osmosis. We're going through the selectively permeable membrane of the water, and now it is going over, because it was that side there's less water, there is higher amount of solute, and now it becomes higher on that one side. There is a hydrostatic pressure which is pressing it to some amount back down, so it's not going completely over, just a little bit. But now it goes a little bit over, and the pressure now necessary to push it over to make it again even, that is the osmotic pressure. And the more solid there is, the stronger that pressure is there. So water wants to go over to the place where the solid is more, and then it goes over and it becomes more, and the pressure now necessary additionally to the hydrostatic pressure, which is already pushing it back down. That is the osmotic pressure. And that is according to Gerard Toga and Senekabowski's Principles of Anatomy and Physiology book on the page 67 and 68. But this is no substitute for medical knowledge. Hi, welcome. I am trying to learn the cytology. Today, osmotic pressure. And after I've done it, we go to shoulder impingement training. And if you participate in the shoulder impingement training, then it's at your own risk. I just noticed I picked to do no osmotic pressure because that is the main thing which we don't understand, which we didn't understood in the form. It's been present, which we didn't understand, I think, which we didn't understand in the 4 parts in which we read already osmosis. But we could do the same also to the other things. Tonicity, hypertonic, hemolysis. Now, osmotic pressure. We have here the big text. We read it already in 4 parts. And in a way we understand it. On the other hand, I think we understand it, but we are not able to imagine it. I think that is the problem. So let's read it and try to understand what is the osmotic pressure. Osmosis is the net movement of a solvent through a selective permeable membrane. In living systems, the solvent is water, which moves by osmosis across plasma membranes from an area of higher water concentration to an area of lower water concentration. So water is the moving of a solvent through the selective permeable membrane. In human beings, that is water through the wall of cells. And it is the net movement. So the movement which actually comes in. Previously subtracted what had come out. Another way to understand this idea is to consider the solute concentration. In osmosis, water moves through a selective permeable membrane from an area of lower solute concentration to an area of higher solute concentration. Yes, they say the following. It is at one place more water and at the other place less water. The reason for is that at the one place there's a lot of other stuff, at the other place only a little of the other stuff. So the water is flowing from a place where there's only a little other stuff in water to the place where there's a lot of water and a lot of other stuff. Water molecules penetrate plasma membranes in 2 ways, via diffusion through the lipid bilayer, as previously mentioned, and through aquaporins, transmembrane proteins that function as water channels. So that's just by diffusion. It just goes through the layer, it just goes through it. And aquaporins, specific proteins which lets water through. Osmosis occurs only when a membrane is permeable to water but not to certain solids. So the osmosis is only happening if water can go through, but other things not. I don't understand what you mean. Why should it be? A simple experiment can demonstrate osmosis. Consider a U-shaped tube in which a selective permeable membrane separates the tube's left and right arm. A volume of pure water is poured into the left arm and the same volume of solution containing a solute to which the membrane is impermeable is poured into the right arm. Both the solutes, which is the dissolved substance, and the solvent, the liquid that does the dissolving, undergo diffusion. I'm right now a bit irritated. What is what? The solvent is the thing which was the blue thing added, I think. A volume of water is poured into the left arm and the same volume of solution. Now we're talking about solutes. I think a solution is a solute containing a solute. So a solution containing solute. Why should a solution contain solute if solute is the substance after it has dissolved? I don't understand it. I can't think of it both ways. Solute, which is the dissolved substance, so the substance which had been added to it and has now dissolved. Or is it the substance in which everything has dissolved? The dissolved substance, we did it already in the previous video. But now I'm confused because of solution. And I don't know where that was. It was here. In a solution, a substance called the solvent dissolves another substance called the solute. The solute is the added thing. In simplest terms, to imagine it. Usually there is more solvent than solute in a solution. It works the other way around. Usually there is more solvent than solute in a solution. In a solution, a substance called the solvent dissolves another substance called the solute. It is dissolving the other thing. For example, sweat is a dilute solution of water. Water is the solvent plus small amounts of salt, the solute. How can we remember that? Solution is the whole thing that is happening between the two, or has happened between the two. And I don't know why, but it always sounds as if solute is the shorter thing, the thing which added the salt in. But I would like to have an explanation of why, or a rule or something. Okay. Solute is the little thing in it, which is dissolving, becoming the dissolved thing and total the solution. A volume of pure water is poured into the left arm and the same volume of a solution containing a solute to which the membrane is impermeable is poured into the right arm. So it is a solution with different things in it, for example, two. The big thing is the solvent and it contains a little amount of solute. Because the water concentration is higher on the left and lower on the right, net movement of water molecules, osmosis, occurs from left to right as water moves down its concentration gradient. At the same time, the membrane prevents diffusion of a solute from the right arm into the left arm. As a result, the volume of water in the left arm decreases and the volume of solution in the right arm increases. The water part goes over but it was already on both sides the same amount of volume, but in one part where there was less water, the water is still going over and becomes in one part more volume as in the other. You might think that osmosis would continue until no water remained on the left side, and that is exactly the problem. I can't imagine it to happen just a little bit. And I would like to imagine it, to see it, or to have an explanation, or a number. Like, it's too small to see it, but it is measurable, or it exists. I would like to have something to understand it. It could be just, it is too small to see it, it is even too small to calculate it, but it is there. That would be enough. You might think that osmosis would continue until no water remained on the left side, but this is not what happens. In this experiment, the higher the column of solution in the right arm becomes, the more pressure it exerts on the side of the membrane. Pressure exerted in this way by a liquid is known as hydrostatic pressure, and it forces water molecules to move back into the left arm. It is not going over, it is not going completely over to the other side. Gravity is pressing it back, the hydrostatic pressure. Equilibrium is reached when just as many water molecules move from right to left due to the hydrostatic pressure as moves from left to right due to osmosis. A solution containing solid particles that cannot cross the membrane exert a force called the osmotic pressure. The osmotic pressure of a solution is proportional to the concentration of the solid particles that cannot cross the membrane. The higher the solute concentration, the higher the solution's osmotic pressure. That is the osmotic pressure. I understand it, but I don't understand it. It is pressing over, and the amount which is there not pressed over, that is the osmotic pressure, because that little part can't go over. We're going to make it in detail in the next part. If you were here for cytology, you can go directly to the next part, where we're going to go to that section there, where we explain now, or say now, what osmotic pressure is, and then we're going to do that. If you stay here and participate in the short impingement training, wir das ja auch, and there should be no pain involved, and this is not a treatment, this is more a prevention short impingement training. If there's at any time pain, then stop immediately, and it's completely at your own risk. Stay good and stable in shoulder circles. Back, up, in front, and down. And back. In the shoulders up. Out, let them fall down. In and up. Out and down. One more time. In and up. Out and down. Now the arms to the sides. And pinch the shoulders together. Pull the shoulder blades together with effort. And now to the outside. Go rather back than in front. To the outside with effort. And in again. And down. And down. Rather more back than in front. Down with effort. And up. With effort. And down. And again up. And now up, in, and out, down. And again up, in, out, down. And down, in. Up, out. rather more back than in front. And down in. And up out. And release. And expand. And the arms again up. Shoulders up. On down. Again up. Shoulders up. And down. One more time. Up. Shoulders up. And down. One arm in front. The other one. And circle the arms up. Back and up around. And that was a short adventure training. I thank you very much and until next time.